Hi, I'm Matthew Henry. I'll be sharing some research on stratospheric aerosol injection modeling. So this is work I'm doing at the University of Exeter. I'm funded jointly by NERC and Silver Lining. And these are all my collaborators, both from Exeter and the US. I'm very thankful to them for their help in doing this research. So we are looking at stratospheric aerosol injection modeling because our projected emissions aren't in line to avoid 1.5 or 2 degree of warming. So we are looking at different ways we could voluntarily, intentionally cool the climate. So there are different ways that people are looking at doing this. One of them is marine cloud brightening, where we brighten clouds that hang above the ocean. The other is thinning clouds, high clouds that act mainly on the long wave side of things, and that would allow more heat to escape to space. But the way that I will be focusing on in this work is stratospheric aerosol injection, where we add, for example, sulfates in the stratosphere, and that would create aerosols which reflect a bit of sunlight and cool the planet. So there have been some previous model intercomparisons of doing stratospheric aerosol injection, but they mainly used equatorial injection, so they injected either at the equator or between 10 north and 10 south. And they used so they went from a high forcing scenario, a high greenhouse gas forcing scenario, and used stratospheric aerosols to bring it down to medium. So it was then later shown that if instead of injecting at the equator, we inject at 4 different locations, we can then use an algorithm that decides each year how much to inject at each location in order to not only maintain the global mean temperature, but also we can seek to maintain the equator-to-pole and inter-hemispheric temperature differences by using these 4 different locations. So as an example, here on the right is the surface temperature change from RCP 8.5 for different latitudes and different years. And then on the bottom is the same simulation, but where we injected at 4 different locations, and using that algorithm in order to maintain the same pattern of surface temperature. So just to talk about the benefits of injecting at 4 different locations and off the equator, I will show some work from Alice Wells, where it's the same scenario, so going from SSP 585, which is a black line here, to SSP 245, which is set to 0 here. And they did it in 2 ways. So one is the blue one, which is injection at the equator, and one is the pink one, which is the P6 sulphur controller, and that is injecting at these 4 different locations shown here, and the total injection shown in pink here. And so you can compare for the same scenario the relative benefits of injecting off the equator. So on the left here, I'm showing the stratospheric aerosol optical depth, which shows that the aerosols tend to get trapped in the tropical pipe in the stratosphere. Whereas for the injection at the 4 different locations, you can do a better job and you can maintain the equator-to-pole temperature difference, which is the pink line here, which is near the 0 line, whereas the black line is the SSP 585 change in pole to equator ratio temperature, and the blue is when you do the injection at the equator. And so, as you would expect from this plot, you get in the case where you inject at the equator, you get an overcooling of the tropics and an undercooling of the poles. So that's the sort of residual temperature change you get in the geoengineered climate. In the case where you inject at the 4 different locations, you still get a bit of undercooling at the poles, but it looks a lot better than in the case where you inject at the equator. And finally, so it is known that doing stratospheric aerosol injection with SO2, you get some stratospheric warming, but the stratospheric warming is a lot stronger if you inject at the equator than if you inject off the equator. And that stratospheric warming has some surface impact. So it's good to know that you could reduce these effects by injecting off the equator. And so this talk is mostly about this new simulation ensemble, where we use that controller with the 4 different locations, and we use a different background scenario, which is arguably more policy relevant. So in this case, the baseline scenario will be SSP 245, and the goal will be to maintain the global mean temperature at 1.5 above pre-industrial, but also to maintain the hemispheric difference and the equator-to-pole difference in surface temperature. So we have 2 Earth system models that have done these experiments, so CESM2 and UKESM1. And the objective of this talk will be to compare the climate impacts and performance of the algorithm. So first off, looking at the global mean temperature. So on the left, we have UKESM, on the right, CESM. And the red is the background scenario, so SSP 245. And then in blue is the geoengineered climate, where we inject aerosols in the stratosphere to maintain temperature at 1.5 degrees above pre-industrial. So the target is shown here in the dashed lines. So both models achieve the required target. Then looking at the second temperature target, which was to maintain the interhemispheric temperature difference. In CESM, there's not much of a change in the interhemispheric temperature gradient. So the controller doesn't have much work to do, so the target is achieved. In UKESM, it's a different story. There's a strong Arctic amplification. So there is a need for the controller to change the injections in order to maintain the interhemispheric temperature gradient. But it looks like it manages to do that. So we do hit the target more or less. And finally, for the equator-to-pole temperature gradient, it's more or less the same story for CESM, where in the background, there isn't much of a change in the equator-to-pole temperature gradient. But in UKESM, where there's a lot of Arctic amplification, there is a large change in the gradient, and the geoengineered climate does not reach its target. And we'll talk a bit more about that later. Yeah, so. And then we can look at the injection rates and the locations. So on the left is for UKESM, on the right for CESM. In black is the total injection rate. And then the different colors show you where the algorithm chose to inject. So it's at 30 and 15 north and south. So in CESM, there's a linear increase in injection for the 4 different locations, and basically most of it is injected at 15 south. In UKESM, it's not so linear, it's a bit more messy, and after 2050, it seems like there's a huge increase in injection at 15 north, and that is basically because the target for the equator-to-pole temperature gradient was not reached, and because of how the algorithm works, it chose to sort of increase the injection at 15 north. And finally, just to give you an idea of what these different numbers mean, I just gave as a reference the Pinatubo eruption in 1991, between 14 and 23 teragrams of SO2 in the stratosphere. And the current tropospheric emissions of SO2 is about 100 teragrams per year. And then we can look at the surface temperature change. So on the left, I'll be showing the UKESM, and on the right, the CESM. And this is for the background warming scenario, SSP 245. And then for the geoengineered climate. So you see for CESM, there's a large North Atlantic warming hole. And so because the algorithms are optimizing for the global mean temperature, it means that the rest of the planet is warming a bit, but not a lot. And in UKESM, because of the large Arctic warming, there's a strong residual Arctic warming, and so the rest of the planet is cooling a bit, but again, not that much. And then you can look at the zonal mean temperature difference. So the solid lines here show the SSP 245 for the 2 different models in green and purple. And the dashed lines show the ARISE, so the geoengineered climate. So there is a strong disagreement between both models in the SSP245 because of the different rates of warming and the different rates of Arctic amplification. But in the geoengineered climate, the disagreement is still there, but it's a lot smaller. And that is basically because the total temperature change is a lot smaller, the effect of the feedbacks is a lot smaller. So the disagreement between the models is smaller. And then, so the story for precipitation is a bit more complicated. So I'm focusing here on the zonal mean precipitation over land, and I'll be separating out the seasons because that is quite important for tropical precipitation. So on the left, I'll be showing the DJF, just December, January, February, and on the right, June, July, August. And the top row here is the SSP245, so the warming scenario. So even then, so the change in land precipitation under SSP245, the two models disagree on the sign of the change in the tropics. So even without stratospheric aerosols. But then if you look in the geoengineered climate, so in June, July, August, the change in the tropics, there's less of a disagreement in the change in the tropics, but in December, January, February, there's more of a disagreement. So the story around precipitation is, I guess, a bit more complicated than the story around temperature change. Okay, so these results are out in the preprint that's out for discussion. So if you have any comments, you're welcome to contribute. And as a side note, I wanted to verify that if I moved the injection further towards the poles, I could reach the targets in terms of inducing enough Arctic cooling to reach the temperature targets that I showed at the beginning. So these are the injection rates I've just shown, where we inject at 30 and 15 north and south. And then this is the sort of a different simulation where I just changed the 30 north and south to 60 north and south. And so in this case, the algorithm just decides to inject everything at 60 north and south, with a bit more at 60 north. So in red is the previous simulations, and then in blue are the so-called like polar simulations corresponding to these. So obviously the aerosol optical depth change is a lot more polar amplified in the case where I inject at 60 north and south. But as you can see, the surface temperature change is not that different between the two cases. And the same is true for precipitation. So I even looked at the different seasons, and the story is more or less the same. So I find it surprising that despite the large differences in the aerosol optical depth, you don't get that much of a big difference in the surface temperature change of the precipitation change. And also just add the blue line here means that you do satisfy the targets as depicted in this plot. So this one in the polar simulations does reach the T2 target. So conclusions, so the adding stratospheric aerosol injection tends to reduce the disagreement between models, at least for the surface temperature change. It's more ambiguous for precipitation changes. And so in order to reduce the uncertainties around stratospheric aerosol injection, it'd be good to have more models performing the same kind of experiments. The algorithm that we used is somewhat complicated to implement. So we're looking at sort of simpler injection strategies that would keep the benefits of injecting off the equator, as I explained at the beginning. Finally, injecting at high latitudes does not seem to change the climate much, so that suggests that at least for UKESM, the number of degrees of freedom around SAI is relatively small, potentially. And so there's a lot yet to be explored using the existing climate simulation ensembles. So something I've been thinking about is the impact on monsoons. So if you want to collaborate on that, please reach out. And if you have any questions or comments, I'd be very happy to respond. And sorry that I couldn't be there either in person or virtually. So thank you very much.